why this makes sense, or at least one model, as far as I know, the best model. Oh, but we should do this question first, before we move on. Reaction A and reaction B have identical frequency factors. However, reaction B has a higher activation energy than reaction A. Which reaction has a greater rate constant at room temperature? Higher activation energy. Is it a larger rate constant or a smaller rate constant? Yes. Reaction B has a higher activation energy. And if you was not intuitive, K is equal to A, which is the pre-exponential factor, E, and that's raised to the negative E over RT. We're told that A is the same, so we don't have to worry about A. You could even just drop it. R is going to be the same for both of these, so we don't have to worry about R. T is going to be the same for both of them. We don't have to worry about T. So really, we just have to think about E raised to the negative activation energy. So if the activation energy is larger, then that would be E raised to a larger negative number, which is smaller. And so then K, because all other things are equal, K will be smaller with a higher activation energy, so reaction A would have a larger rate constant. The theory for all of this is collision theory, which makes sense, at least for the most part. For most reactions, this is the case. Collision model treats all of our atoms and molecules as little particles that have to collide in order to react. And so we have all of this theory, we have these equations, we can do experiments, we can match that to reality, we can calculate things, and we can use those calculations to predict things also. That's like the true determiner of a good model. But it doesn't really explain like the why of anything. It's more like a law. I mean, it's called the rate law. So it makes predictions, but it doesn't necessarily explain why the law works the way it does. So the collision model or collision theory is an explanation for, well, why does the rate law work? And we're treating all of these particles as if they need to collide. And that makes sense because in the case where we've got something like A and B have to react to form products, as we'll see later, we can't necessarily determine from an overall reaction. But if we knew that this was the only step in the reaction, then an A molecule has to collide with a B molecule in order for it to react. The overall rate order might be second order. And if this is a single step, right, the concentration of A would matter and the concentration of B would matter because those need to collide. More A, higher reaction, more B, higher reaction. So you can think of this like a demolition derby. I'm actually going to switch over here and we're going to listen to Hank Green for a little bit, assuming this works.
People driving cars around the field doing their best to ram into each other while protecting themselves as much as possible. The goal, of course, is to damage the other cars so badly that they can't be driven anymore to the driver of the last operational car. You know ground scores chemistry well enough to know that I probably wouldn't have mentioned this if it was some relation to chemistry. So yeah, it does. Chemical reactions basically work just like this. Atoms and molecules move around their environment, occasionally ramming into each other. If they do it just right, a reaction happens between them, and if enough of them do it, the concentration of the reacting molecules will go down, while the concentration of the products goes up. Wait, but it's not as simple as it sounds. For demolition drivers or for chemicals, in both cases, a lot of the collisions that occur have very little effect on the end result. One molecule hitting another doesn't mean a reaction is going to take place. In the same way that just randomly bumping into another guy's car doesn't mean that you're going to ram him out of the derby. So what makes a collision effective? The hit has to be hard enough and it has to be aligned just right. The branch of chemistry that studies how these collisions affect the rate of reactions is kinetics. And if you ask me, it's just as exciting and a heck of a lot more useful than demolition derbies. If only they sold funnel cakes in chemistry class.
It would be so great if I had funnel cakes right now. I don't have funnel cakes, I'm sorry. So, back over to here. So yeah, like a demolition derby, our atoms and molecules have to collide with enough energy to react and in the correct orientation to react. And so we've got two factors, and actually highly recommend, as an overview, the crash course videos are excellent. They give you just the really fast overview. I should probably assign them before lectures, because then you get the overview and then you come in and we talk about the details. So in our collision model then, we're thinking about these atoms and molecules, they need to collide, and that corresponds to these different parts of the Arrhenius equation. In the Arrhenius equation, we've got this orientation factor, or we've got the pre-exponential factor, which was the A before, but it turns out that A actually consists of two things. Or was it called the approach factor? But the orientation factor and the collision frequency. So orientation factor is related to how often, or actually how likely it is that two atoms or molecules will collide in the correct orientation. So for some reactions, it's very simple. If I've got two atomic species that are both spheres, there's not really an incorrect way that they could collide. If they collide, they collide. So you'd have an orientation frequency close to 1. But if I have really complicated molecules, maybe like sucrose, and that's trying to react with something else, might need to collide in exactly the right way, and so we might have a very low orientation factor because it's very unlikely that they actually collide with the correct orientation. And then collision frequency is just the number of collisions per unit time. So how often do they actually collide? So even if we had, or actually, say, if we have 10 to the 9 collisions per second, which is a lot of collisions, was a billion collisions per second? If my orientation factor is close to 1, then pretty much getting a billion correct collisions per second, and then the only thing that matters is how much energy they have. But if we've got complicated molecules and our orientation factor is really small, then that's going to reduce this 10 to the 9, and our overall pre-exponential factor will be a lot smaller. So in the case of these molecules, we've got nitrogen, well, nitrous chloride probably, where these nitrogen, oxygen, chlorine molecules have to, or react to form nitrogen monoxide and chlorine gas. The collision has to happen in just the right way. So sometimes you can interpret this just from the shapes of the molecules. So for example here, if I want these chlorines to end up bonded together and separated from their nitrogen monoxides, then the chlorines probably need to be the things that collide. Now you can't really predict exactly all of the different ways. Well, in this class, we're not going to predict exactly all of the different ways that they could collide and which ones of those are correct and which ones are incorrect. I'll give you simpler examples if I write a problem like that. But in this case, we can look at sort of just a few different ways that they collide. So if they collide oxygen to oxygen, or actually, sorry, nitrogen to nitrogen, then they're not going to react. If we collide nitrogen to chlorine, that's not an effective collision. We need the chlorines to collide. So our orientation factor for this reaction would be 0.16. So on the lower end. a lot less than half, less than a quarter. It's not 1/9. It's like 1/7. Yeah.
Like the oxygen and the oxygen collide, they don't make O2.
Not necessarily. That might be a possible reaction, but it might have a much, much higher activation energy.
Because it's harder to separate nitrogen from oxygen.
It's like not important for this. Yeah, it's possible that if they collide in a different orientation that we could get other reactions, but if that activation energy is too high, it doesn't matter how good the orientation factor is. Or if they collide at all, right? So then this is actually, tie this into other stuff in chemistry, especially organic chemistry. In organic chemistry, you've got a lot of molecules that could react a lot of the time, and you don't want to, well, you can increase the heat to increase the speed of your reaction, speed things up, save you some time. But as you increase the heat, yes, we get other collisions, and those other collisions, if there's enough heat, might cause side reactions to happen, stuff other than the product that we want. Yeah. And at some point, if you add enough energy, you'll just ionize them all and it'll become a plasma. Just break all the bonds.
Is P something that can only be found experimentally? Or is that something we will predict?
We can predict it for simple things, and I'm sure there's modeling to say, but we got to determine more about, we'll talk more about like how to determine the reaction mechanism in a bit. That's a good question though. I imagine it can be modeled but you need to know which things actually react, and you might create intermediates before you create the final product. And we'll talk about that next. Yeah. So yeah, if you add enough energy, you could get other reactions, but usually you try to adjust the temperature so that you're getting as fast as possible the reactants that you, or the products that you want. Avoid side reactions. So very small orientation factor indicates that there's a very specific way that things need to be aligned. Reactions between atoms usually have a orientation factor of about 1. So individual atoms, because they're spheres, there's not really a wrong side of the sphere. You could have glancing reactions maybe, but then that might be more related to the energy. You can have orientation factors that are greater than 1. And there was an example here, so the textbook has an example, and this is actually really cool. So there's this reaction between potassium gas and bromine gas has an orientation factor of 4.8, which means that the molecules don't even need to collide in order to react. And the proposed mechanism is this harpoon mechanism, which the book describes as a bromine molecule gets near to a potassium atom, the electrons of the potassium atom act like a harpoon and spear one of the bromines, giving it a charge, and then the opposite charges, the Coulombic forces, draw them together. And so it basically spears a bromine and then reels it in, and then it reacts. So it doesn't even have to collide, they just have to get close, which is why our orientation factor is larger than 1. Oh, that was neat. But for most things, 1 or less. Actually, I should say, for most things, less than 1. So this is an example of a kind of problem that I would give you, where, say, which of these would you expect to have the smallest orientation factor? Usually, if it's more complex, then it's going to have a lower orientation factor. And so one way that you might approach this is you could draw out some pictures. So if I have hydrogen and iodine, like atoms, that's where our orientation factor is going to be close to 1, because not an incorrect way for them to react. If I have hydrogen, I should use different colors. If I have hydrogen molecules and I have, or molecular hydrogen and molecular iodine, then they probably need to collide side on rather than colliding from end to end. So there's different ways that they collide, which means that there's probably one of those ways is the way that they react and the other is not. So there are kind of two ways. You can go side on or you go end on. But then for hydrogen chloride, pick a different color. Oh, hydrogen, I did blue. If I have to react two of these, and I want to get H2 and Cl2, again, they probably have to collide end on in order to react so that the hydrogen can be close to the hydrogen and the chlorine can be close to the chlorine. But if they collide end on this way, that's going to be wrong. If they collide end on this way, that's going to be wrong. And this isn't going to let me rotate, but I can do it if I do this. They can also collide this way, which would also be incorrect. So there's more incorrect ways that they can collide. So C would have the smallest orientation factor. All right, so we got collision theory out of the way. They have to collide in the same correct orientation. And then frequency also plays a factor. But if we wanted to determine what that factor is, orientation factor, we have to know first what is actually reacting and happening in our reaction mechanism. Because even though we write overall reactions, because we know what the reactants are, put them into the reaction, and we know what the products might be because we pull them out when the reaction's over, they might take intermediate steps to get to that final product. In fact, most reaction mechanisms do. So our overall reaction here between hydrogen and iodine chloride might take place in a single step, might take place in multiple steps, and our reaction mechanism is going to be the series of individual chemical steps, which we can represent as their own chemical equations, in which the chemical reaction likely occurs. I say likely because these are all proposed. You can't really determine if the reaction mechanism is, you can't prove that it's correct. And so we'll have elementary steps, which are those individual steps that represent the actual collisions happening that drive the reaction forward. So to pull apart this reaction, the mechanism, we have two steps. In our first step, one of our hydrogen atom, or molecular hydrogens, reacts with iodine chloride, and we get hydrogen iodide and hydrogen chloride. Monochloride, I guess I should say. But HI, and then we have HI reacts with an ICl, which is one of our original reactants, to form HCl and I2, giving us the final products. So our original reaction would have been, for the overall, H2 plus ICl, or 2ICl, gives us 2 HCl plus I2. So when we're proposing a reaction mechanism, there's a few things that you have to check for to make sure that it is a valid mechanism. One of them is it has to equal the overall reaction, because obviously if it doesn't equal the overall reaction, then how could it represent the real reaction? So the steps here, if you remember back to Chem 1 and Hess's law, was at least one example of this, where you can add up the reaction equations, stuff cancels out on the sides, and you end up with a new overall equation, and you can calculate the energy of the reaction. You do that in Chem 1, right? Yeah, okay. So here, if I add these up, I can see I've got HI on either side. So those cancel out. These HCl's will add together, which gives me the 2HCl. These ICl's add together, which gives me 2ICl. And so this represents our overall reaction, so this is a valid mechanism. Or at least as far as we know right now. And the things that cancel out in the middle are our reaction intermediates. Reaction intermediates, honestly, remembering back to taking this class originally, this is one of the things that I remember, and it was like, how do you come up with these reaction intermediates? We'll talk about that, but they don't exist in the reactants or the products because they exist for an intermediate step, and then they get used up before the end of the reaction. So a reaction mechanism is trying to paint the entire picture of what is happening in the reaction. It should also correspond to our rate law. It shows the individual collisions that occur, and we can use chemical kinetics or the rate law for an equation, which is determined experimentally, to figure out if a mechanism is correct or to give us hints about what the actual mechanism is. So we measure the kinetics of the overall reaction, figure out the order of the reaction with regards to each of the reactants, then use that to piece together a possible reaction mechanism. So we can look at these elementary steps and we characterize them based on the number of reactant particles involved in the step. So unimolecular would be one reactant forming some products. Bimolecular, where we've got two reactants, which could be two molecules of the same or two separate molecules. So unimolecular would be some kind of decomposition. Bimolecular would be the more typical two things reacting together to form a product. And then there are termolecular steps, which would be three different things that have to collide simultaneously in order to make a product. And they are very rare. It's kind of like whenever you try to plan something, the more people that you add to that plan, the more complicated it becomes to try and get everybody to the same spot at the same time, or even find a time where everybody can meet. Imagine that, but now it's atoms and molecules that are moving randomly in every single direction. The frequency with which those three things will collide all at the same time with the correct orientation becomes almost impossibly small. Not impossible, but almost. So if you're ever writing a reaction mechanism, probably bimolecular steps, sometimes a unimolecular step. In this class, never a termolecular step, because they're so rare. So unlike overall reactions, we can only determine the rate law for an overall reaction from an experiment. When we're talking about our intermediate steps, we can deduce the rate law from the intermediate equation. Just think about why can we do that for an intermediate reaction step, but not for the overall. Actually, let me even zoom in here. So like if we just look at this one, why can I look at a reaction that says A plus A equals products and say that the rate is A squared, concentration of A squared? But I can't do that for an overall.
Because for the overall, there might be intermediate steps that aren't being taken into account.
Yeah. The overall is a black box. When we look at the overall, we just say, I know I put these reactants in, I know I get these products out. How that happens is completely hidden. And so there might be intermediate steps. There's a lot of stuff that we just can't know. So it's not possible from that overall to be able to determine what those intermediate steps are or what the overall rate is. But when we're talking about intermediate steps, we're thinking in terms of collision theory, and we're trying to hypothesize what are the actual collisions that are occurring. And when we're thinking about this in terms of individual collisions, if I need A to react or collide with an A, then the rate of the reaction depends on the concentration of A. Or maybe it's better to look at this next one. Let me move this down to A and B. Right, so overall rate here is still second order. But I need A and I need B, and I need those both to collide together in this proposed intermediate step. And so, of course, the concentration of A is going to matter and the concentration of B is going to matter. So in an intermediate step, we're thinking about the actual collisions that are happening, whereas in an overall, we've hidden all of that information. Because we don't know what the collisions are, we just are using observed experimental data to determine the rate law. I think this is one of the reasons, actually, while I was looking at it this morning, I was like, oh, this is actually one of the reasons that I really love chemistry, because it's right at the limit of what we can theorize and what we can experiment on. And this is a perfect example, because we do an experiment that determines a rate law, and then we have to use theory to explain it by coming up with these intermediate steps that will add up to that rate law and match the reality that we observe. It's a fun puzzle. Okay, so, right, so we can deduce the rate laws for our elementary steps, for our intermediate steps. Usually, almost always, for a reaction, there's going to be a rate determining step. The rates of the reactions or intermediate steps are going to occur at different rates. They might both be really fast, but if one of them is slower, that's the rate determining step, right? So any difference in rates makes one of them rate determining. And it's kind of like when there's construction, which right now there's construction on Caldwell, and it's really annoying because I have to, well, I just avoid Caldwell now. But when I'm driving home, everything narrows down into a single lane, and it takes forever, and the lights are dumb. They're just on timers. But basically, everything up to that point is fast, and then everything after that, or actually, everything at that step is really slow, and then after that, things can be fast again. It's also like this, I don't know if you've seen this picture before. It's 50 lanes that can then goes through a toll booth into 20 lanes. I think they've since fixed this, but for a while, this was a reality in China. It's crazy. There's been some really bad, and then this is one of those things where it's like, so you have this, which causes delays, and then cars are idling too long, and they're idling near other cars, so it gets really hot, and then cars break down, and then you've got broken down cars plus the toll gate, and then more cars break down, and then you're just stuck. You just, yeah. And this is why we need public transit. So this is our rate, there's always going to be a rate determining step, almost always a rate determining step. And that's important when we're trying to think about, well, how do we come up with the reaction mechanism? How do I figure out what the elementary steps are? The fact that we have a rate determining step is a huge hint at what the overall mechanism will be. So we have this overall reaction, and we do the experiment. We figure out that the rate law is second order with respect to nitrogen dioxide, but does not depend on the concentration of carbon monoxide. Could this be a single step reaction? And I know if you already downloaded the slides, then you can already see what's underneath the washi tape, but think about it. If this occurred in a single step, shouldn't the rate of, or the amount of carbon dioxide or carbon monoxide matter? Wouldn't that be part of the overall rate if carbon monoxide is involved in the collision? But it's not. It's missing from the overall rate. And that's a hint that this occurs in multiple steps, that there are elementary steps. It also tells us something about the elementary steps. So if we know that this occurs in 2 steps, is carbon monoxide, or actually, think about this. Is carbon monoxide part of the first step? Or the slow step? Carbon monoxide would be part of the faster step because the concentration of carbon monoxide is not determining the reaction rate, which is why it's not part of the overall rate law. Doesn't mean that it's not part of the reaction. It is part of the reaction. Oh, I have to switch to you. So annoying. So our first step is actually just nitrogen dioxide reacting with nitrogen dioxide. And also importantly here, it's not just that that's the first step, but it's also the slow step. And because the slow step is this choke point in my reaction, that slow step will always be the rate determining step. Which is why the overall rate doesn't contain nitrogen or carbon monoxide. So the way to approach this would be, we see the overall rate, we do the experiment. We know that our overall reaction is using nitrogen dioxide and carbon monoxide. And we know that it's producing nitrogen monoxide and carbon dioxide. With these 2 pieces of information, then, we look at our rate and we say, okay, well, there's obviously a slow step. And that slow step has to be 2 nitrogen dioxides reacting together. The other reason we know it's 2 nitrogen dioxides reacting together is because this is actually the rate of this step. So the rate of our first elementary step will be K1. And because we can use, or we can deduce or infer the rate law of elementary steps, the fact that nitrogen dioxide is squared tells us that it's nitrogen dioxide reacting with nitrogen dioxide in the slow step. That creates some intermediates. And then really what we have to do from there is figure out, okay, so that's my slow step. Now, carbon monoxide has to be involved in this. And I also have an intermediate, which is the nitrogen trioxide, which is not part of my final reaction. So nitrogen trioxide has to disappear before this reaction is done. And so we could guess that nitrogen trioxide would be one of these reactants. And it's probably going to react, in this case, kind of cheating because we know it's 2 steps. Has to react with a carbon monoxide to make we already got to get the nitrogen monoxide. Oh, it'll make another NO2 plus CO2. Because we need this CO2 because we know it's in the overall reaction. We need carbon monoxide in the reactants because we know it's one of the reactants. And we're canceling out the nitrogen trioxide because it's an intermediate and it's not in the overall reaction. And so that is our fast step. And then we can look at these and say, okay, I want to erase this one now because we have that. If that's the case, nitrogen trioxide cancels out. One of my nitrogen dioxides cancels out. And so I get back the overall reaction that I expected from the experiment that I did. Any questions? It's a puzzle. Love puzzles. So, in the case of this reaction, actually, the rate limiting step here is the rate limiting step because it has a higher activation energy. So if we look at this reaction coordinate diagram, the activation energy is from the starting point of our reactant up to the peak of the transition state, right? That's the hill that you have to get over. We then get an intermediate state, which is in the middle, and the activation energy of that intermediate here is going to be from that transition state to the peak of, or I guess from the intermediate to the peak of the transition state, which is a much, much smaller activation energy in this case. So pretty much as soon as this reaction happens, everything else happens really quickly to get to the products. So the easiest of these is when it's a single or when it's two steps and it's the first one that's slow. When the first step is slow, then the overall reaction or the overall rate law for the reaction will be the same as the slow step. Because that happens first, everything else happens after that. It actually doesn't even really matter if there's more steps because they all happen fast anyway. It won't determine the rate. So the conditions that have to be met for a mechanism to be good is the elementary steps in the mechanism must sum to the overall, and the rate law predicted by the mechanism must be consistent with the experimentally observed rate law. Mechanisms can't be proven because we can't observe them directly. Can't put little tags on them and watch the little atoms and molecules react and go through their whole dance and become products. There can be a lot of clues. We can build evidence for whether or not our mechanism is valid, but you can't prove the mechanism. So when the first step is the slow step, that's the easiest, but what if it's not the slow step? What if our first step is fast? When the first step is fast, or really when the first step is not the slow step, we end up with an interesting situation where we now have we have a big open freeway and then a traffic jam, and then we can have a big open freeway after that. And what happens is actually you end up with an equilibrium between reactants and products for that first elementary step. We haven't covered equilibrium yet, but essentially we're going to be forming as many products in that initial elementary step as possible, and then that concentration remains unchanged, and therefore it doesn't affect the rest of the reaction. But what this means is that, well, actually, we'll go to the example. It means that in our first step, we have our reactants and we create products, but those products, in terms of the overall reaction, actually, let me write this. We'll create products, which might be part of the overall reaction, but it can also create intermediates. Those intermediates only exist as a step in the reaction. And so that means that the second step will be some combination of intermediates and reactants that then goes on to produce products and could produce more intermediates. So the problem here is then I can't have these intermediates as a part of my overall rate law because they're not part of the overall reaction. So to see a more concrete example of this, I've got hydrogen reacting with nitrogen monoxide creates water and nitrogen. In this reaction, I've got my first step here is fast. My second step is slow. This step then is the one that will determine the rate. This is the bottleneck. This first part will go really fast, create a lot of dinitrogen dioxide. That dinitrogen dioxide will then hang out in a stable concentration until it gets used in the second step. As soon as the second step happens, then the third step happens really fast. So there's basically none of the intermediates that might be here in our products. They get used up immediately. So then the problem is, if I wanted to write an overall rate law from just the second step, it would be hydrogen to the first and dinitrogen dioxide to the first. But dinitrogen dioxide is not part of the overall reaction. So we got to do a little bit of rearranging. I guess we can first show that our elementary steps add up to the overall. So if we propose this mechanism, I want to keep this and these. This cancels, and so I get all of these that add up to the correct reaction. All right, so then we need to show the next part that the rate law of our predicted mechanism or proposed mechanism will match that of the overall experimental rate law. And this is where we have the problem with dinitrogen dioxide. Dinitrogen dioxide is an intermediate. We can't have that as a part of this reaction, but we could use the fact that this first step is going to be in equilibrium. The key is that when something is in equilibrium, the forward rate is equal to the reverse rate. And when we're talking about multiple elementary steps, we might express that as forward rate for the first step is going to be rate sub 1. So rate 1 is equal to rate negative 1. So the rate 1 is the rate of the first elementary step going forward. Rate negative 1 is the reverse rate of the first elementary step. And again, for elementary reactions, we can write out the rate laws. So we could say rate of the forward should be K sub 1 using the same subscript, NO squared. I can say the rate for the reverse, not 2, negative 1 equals K, the negative 1, times dinitrogen dioxide to the first. So now I can use the fact that rate 1 is equal to the reverse of rate 1 and set these equal to each other. I guess I've introduced the solution before I really showed you the problem. Because if we want to write the rate for the slow step, I need another page. If we want to write the rate for the slow step here, the rate of this step would be K2 times the concentration of H2 times N2O2. And the problem is that concentration of N2O2. We can't have our overall rate dependent on that intermediate. But I can get rid of that intermediate and instead use my reactant, which is the nitrogen monoxide. If I rearrange this to now be K1 over K negative 1 times NO squared. Now that is equal to concentration of dinitrogen dioxide. And then I take my rate 2 equals K2, H2, and I replace the dinitrogen dioxide with this thing that is equal to dinitrogen dioxide. We're kind of indirectly getting to this, but the rate constant of the overall reaction is a combination of all of the rate constants. So now my overall rate I'll write it out this way first. K2 times K1 over K to the negative 1 times H2 times NO squared, or the overall rate is K times hydrogen concentration times nitrogen monoxide squared. And the key to all of that is knowing that in my first step, which is fast, I'm going to reach equilibrium so that those rates are now equal. And when those rates are equal, I can set the rate laws for the forward and reverse reactions equal to each other, which I did in this step, and then over here. And then I can rearrange that to replace the concentration of my intermediate in the slow step rate law.